Monoidal categories and their representations. Lecture 7. Cells and Perron-Frobenius Theorem. Let's recall the discussion about the Grothendieck ring of a monoidal category from the previous lecture. Let C be a monoidal category. Assume that C is essentially small, additive, and Krull-Schmidt. In particular, it is idempotent split. Assume also that the tensor product in C is biadditive. Denote by C in bracket and with the direct sum sign on the right the free module over the integers with basis given by the set of the isomorphism classes of indecomposable objects in C. Then we have the multiplicity map, which takes as an input some object in C and gives as an output the list of the multiplicities in this object of all indecomposables. So the output is then an element of our free Z module. Then we can define on this free Z module the structure of a ring. And this is defined using the tensor product. If we have the list of the multiplicities in some object X and the list of multiplicities in some objects Y, then we multiply these two lists in the following way. So their product is defined as the list of the multiplicities in the object X tensor Y. So this defines on our free Z module the structure of a ring. And this ring is called the Grothendieck ring of C. The Grothendieck ring of C comes equipped with the distinguished bases. The bases given by the representatives of the isomorphism classes of indecomposable objects in C. This basis is positive in the sense that all structure constants with respect to this basis are non-negative real numbers. In fact, they are non-negative integers. Now we have arrived to the definition of cells. For two indecomposable objects X and Y in C, we will write that X is left greater than or equal to Y, provided that X appears with a non-zero multiplicity as a direct summand of M tensor Y for some indecomposable object M in C. It is easy to see that this defines a partial preorder on the set of all isomorphism classes of indecomposable objects in C. This preorder is called the left preorder. The equivalence classes of the left preorder are called left cells. So we know that this is really a preorder. Two different elements might turn out to be left equivalent. Similarly, we can define the right preorder. So we will say that X is right greater than or equal to Y, provided that X appears with a non-zero multiplicity in the tensor product of Y with some other indecomposable object. This defines another partial preorder called the right preorder, and the equivalence classes with respect to this preorder are called right cells. Similarly, we can define the two-sided preorder. Given two indecomposable objects X and Y, we will say that X is two-sided or J greater than or equal to Y, provided that X appears with a non-zero multiplicity in the tensor product of M with Y and with N for some Mn in C, or in the set of indecomposable objects of C. Again, it is easy to see that this defines a partial preorder. It is called the two-sided preorder, and the equivalence classes for this preorder are called two-sided cells. Since we have the identity object in C, then if X is left greater than or equal to Y, then X is two-sided greater than or equal to Y, because we can take N to be the identity object in the definition of the two-sided order. And similarly, right-related objects are also two-sided related. So this generalizes the notion of Green's relation for semigroups, which originate from the paper by Green, which is called On the Structure of Semigroups from 1951. In the context of multivalued operations, this was discussed in the paper by myself and Gana Kudryavtseva, which is called On Multi-Semigroups in 2015. So let us discuss some examples. First, an observation. If the identity object I is indecomposable, then it is both left, right, and two-sided smaller than any other indecomposable object X in C. This is obvious directly from the definitions because I tensor X is isomorphic to X regardless on the order in the tensor product. So here is a detailed example. Let G be a finite group and K an algebraically closed field whose characteristic doesn't divide the order of G. Consider the semi-simple rigid monoidal category of all finite-dimensional G modules. Then, by Maschke's theorem, the indecomposable objects in this category are exactly the simple G modules. If V is a G module, then we know from our discussion of rigid monoidal categories that the trivial G module appears as a direct summand of V tensor with the dual G module V dual. This implies that any indecomposable G module V is left, right, or two-sided smaller than the trivial G module. Combined with the first line of the slide that the identity object is left, right, or two-sided smaller than any other indecomposable objects, we obtain that in this example, the set of indecomposable objects of C forms exactly one left cell, exactly one right cell, and exactly one two-sided cell. So all objects are both left, right, and two-sided related. So here is another example. Let K be an algebraically closed field. Let A be a finite-dimensional K algebra. Assume that the algebra A is connected in the sense that the Gabriel quiver of A is connected. This is equivalent to saying that the regular AA bimodule A is indecomposable as an AA bimodule. Consider the monoidal category of all AA bimodules. Let E1, E2, and so on Ek be a complete and irredundant list of primitive idempotents for A. Then the indecomposable projective AA bimodules up to isomorphism are exactly the following bimodules. So we take the left projective module AEI and we tensor over the field with the right projective A module EJA. And I and j here vary between 1 and k. So we have k squared indecomposable projective AA bimodules up to isomorphism. For these bimodules, we have the following tensor product formula. When we tensor AEI tensor EJA, so when we tensor this bimodule over A with the bimodule AES tensor ERA, then the outcome is isomorphic to the bimodule AEI tensor ERA with the multiplicity given by the dimension of the vector space EJAES. This is a tensor product formula which is very easy to obtain. Now let us consider inside the category of all finite dimensional AA bimodules, let us consider the additive closure of the regular AA bimodule A together with all projective AA bimodules. From the tensor product formula, we see that this additive closure, which we denote by CA, is a full monoidal subcategory of A mod A. So indeed, the regular bimodule is the identity object, so tensoring with it does nothing, and this formula implies that projective bimodules are actually closed with respect to the tensor product. So this gives us a monoidal subcategory inside A mod A, and one usually calls this monoidal category CA the monoidal category of projective AA bimodules. This term is slightly misleading because the regular bimodule is not projective unless A is a simple algebra. So we assume that A is connected. So the identity bimodule is projective if and only if A is simple in this case. So let us assume that A is not a simple algebra to avoid this trivial situation. So from the tensor product formula, we immediately see that our category CA splits into two-sided cells. One of them contains the identity bimodule, which is not projective under our assumptions, and the second two-sided cell, it contains all indecomposable projective AA bimodules. Of course, the first cell Ji has only one element, so it's both left, right, and two-sided cell in its own right, while the second cell J further splits into the left cells. So the left cell Lj, so we fix the index J for the second component of the tensor product, and we vary the index I for the first component. So we have exactly K, so we have K primitive idempotents for A, and so we have exactly K left cells inside J. And similarly, we have K right cells inside J, where we fix the index in the first component, the index I, and then we vary the index J in the second component. So this is an explicit example on how cells look in this particular monoidal category. Now let us talk about the Perron-Frobenius theorem. Theorem due to Perron and Frobenius. Let A be an n times n matrix with positive real entries. Then the following holds. Claim 1. There is a positive real number R called the Perron-Frobenius eigenvalue, which has the following properties. R is an eigenvalue of A, and any other eigenvalue lambda of A, possibly a complex eigenvalue, satisfies the following inequality. The absolute value of lambda is strictly smaller than R. Claim 2. The Perron-Frobenius eigenvalue R is simple, that is, it has algebraic multiplicity 1. Claim 3. There is an eigenvector V of A for the eigenvalue R, such that all entries in this vector are positive real numbers. And claim 4, any eigenvector of A for any eigenvalue which has non-negative real entries must be a scalar multiple of this eigenvector V. Proof. Let us start by actually defining R and V. So let delta be the set of all vectors in Rn with non-negative coefficients such that the sum of the coefficients is exactly 1. So this is the standard simplex in Rn. Note that the set is convex and compact. Also, for any element x in the set, the vector Ax is non-zero because all entries in A are positive, and the vector x is a non-zero vector. Now we can consider the map which takes a vector x from our set delta and sends it to the vector Ax divided by the sum of all coefficients in Ax. By definition, the outcome is again a vector in delta, so this is a map from delta to delta, and obviously this map is continuous because the denominator can never be zero, because Ax is a non-zero vector with non-negative real coefficients. So, by the Brouwer fixed point theorem, there must be a fixed point. Let's call this fixed point V. So V is an element in delta such that if we apply A to V and divide by the sum of the coefficients in the outcome, we will get V. So by definition then, V is an eigenvector for some positive eigenvalue. Let's call this eigenvalue R. Since all entries of A are positive, it follows that all entries of V are positive. because if v is a non-zero vector with no negative real coefficients and we multiply it with a, the outcome will have positive real coefficients. So all entries in v are positive numbers. Now let us discuss the simplicity of this eigenvalue r, which we just established. Assume w is another real eigenvector for this eigenvalue r. Choose I to be such that the value of wi, so this is the ith entry in w, divided by vi, this is the ith entry in v, is minimal as a real number among all i's. This is well defined because all vi's are positive, by the way. And now we can consider the linear combination of w minus a times v. And since it's a linear combination of two eigenvectors for the eigenvalue r, it is an eigenvector with this eigenvalue. All entries of this eigenvector are non-negative because of our minimality of a, and the ith entry is 0, again by the definition of a. So this vector must be the 0 vector, and in other words, v and w are linearly dependent. So r is indeed a simple eigenvalue. Now let us look at the spectral radius of a. So consider the spectral radius ρ of a. So since we already know that a has an eigenvalue which is real and greater than 0, the spectral radius of a is greater than 0. So we can consider the matrix B, which is obtained from A by dividing A by its spectral radius. So the matrix B has spectral radius 1. And again, this is a matrix with positive coefficients. Assume that a matrix B has an eigenvalue, a possibly complex eigenvalue lambda, which is different from 1, and such that the absolute value of this eigenvalue is equal to 1. Then, of course, there is some positive integer power m, such that lambda to the power m has negative real part. Let us choose epsilon, a positive real number, which is strictly smaller than all diagonal elements in the matrix B to the power m. Consider the matrix C, which is equal to B to the power m minus epsilon times the identity matrix. By our choice of epsilon, this matrix has positive real entries. If x is an eigenvector for b to the power m, with the eigenvalue lambda to the power m, which exists because lambda is an eigenvalue for b, then x is an eigenvector for c with the eigenvalue lambda to the power m minus epsilon, because of the definition of c. However, we know that the real part of lambda to the power m is negative. Therefore, the absolute value of lambda to the power m minus epsilon is greater than the absolute value of lambda to the power m, which is 1. This means that the matrix C has an eigenvalue whose absolute value is strictly greater than 1. Now let us look at the matrix C closer. We constructed C so that all entries in C are positive. However, they all are less than or equal to the corresponding entries of b to the power n. Let us now recall Gelfand's formula. If we have any square matrix M and any matrix norm, then the spectral radius of M is equal to the limit where k goes to infinity, and then we should take the norm of M to the power k and then take the k's root out of this value. So now we can take, for example, the matrix norm given by the maximum of the column sums. For this matrix norm, it is obvious from the definition, since all entries of C are bounded by the corresponding entries of b to the power m, that the norm of C to the power k will be bounded by the norm of b to the power m to the power k. So therefore, using the Gelfand's formula, we deduce that the spectral radius of C is bounded by the spectral radius of b to the power m. This in turn is bounded by the spectral radius of B to the power n, which is equal to 1. And this contradicts to the fact that we have found an eigenvalue for C of absolute value strictly greater than 1. So this implies, in particular, that the spectral radius of A is an eigenvalue for A. So the spectral radius of A, it's a real number, and it is an eigenvalue for A. So now we have to connect our definition of R and V with the spectral radius for A. If we look at the transpose matrix of A, it also has positive coefficients, and of course the spectral radius of the transpose of A is equal to the spectral radius of A. Let W be a positive eigenvector for the transpose with some eigenvalue mu. It exists, we just established it. Let V prime be a positive eigenvector for A with some eigenvalue lambda. Then mu times W transposed times V prime, so mu times W transposed is equal to A transposed times W. So we can rewrite it as W transposed A times V prime. And now AV prime is lambda V prime, so it is lambda W transposed times V primed. And from here, since both W and V are positive vectors, so their product is non-zero, it follows that mu is equal to lambda. So in particular, we deduce that R, for which we have a positive eigenvector, should be equal to both mu and lambda. In other words, V is the only positive eigenvector for A, up to a positive scalar. So this establishes the uniqueness of the positive eigenvector for A. And in order to prove Perron-Frobenius theorem, it remains to prove that our eigenvalue R is equal to the spectral radius of A. So here is how we're going to do this. Let us consider our space Rn as a standard Euclidean space. Take any positive vector x and consider the following sequence. We start from x, denoted by x0, and then define xi as A applied to xi minus 1 divided by the length of A applied to xi minus 1 for all I greater than or equal to 1. So then this sequence, it's a bounded sequence in Rn, and so it has a convergent subsequence by the Bolzano-Weierstrass theorem. The limit of this convergent subsequence is a non-negative, and hence positive. We know that the eigenvectors are positive. So it's a non-negative eigenvector, and since such an eigenvector is unique, it must be a multiple of V. So it remains to show that if we choose x generically, the limiting eigenvector must be rho of A. Clearly, the set of all positive vectors of length 1 generates Rn as a vector space. In particular, there must be at least one positive vector, or actually generic positive vectors, cannot be written as a linear combination of the vectors if we take a Jordan basis for our linear operator A and pick up in this basis all those vectors which correspond to generalized eigenspaces for all other eigenvectors except for the eigenvalue rho of A. If we take such a generic vector x, then of course the eigenvalue for the limiting eigenvector in our sequencing procedure must come from the maximal eigenvalue in the matrix A. And this eigenvalue is of course rho of A. So this completes the proof of the Perron-Frobenius theorem. So here are some extra claims which one can add to the Perron-Frobenius theorem, which we are not going to prove. Claim 5. If V is a Perron-Frobenius eigenvector for A, and W is a Perron-Frobenius eigenvector for the transposed of A, which we normalize such that the W transpose times V is equal to 1, then the limit for k approaching infinity of A to the power k divided by R to the power k, so here R is the Perron-Frobenius eigenvalue, this is equal to V times W transposed. Claim 6. which is called the Collatz-Wieland formula, the Perron-Frobenius eigenvalue R is equal to the maximum taken over all non-zero vectors x in Rn with non-negative coefficients, and we take this maximum over the following expression: the minimum over all I for which xi is non-zero, and then we take the sum over all j from 1 to n, aij xj, and we divide it by xi. So the numerator here is just the ith component of the vector a times x. We take the ith component of that vector and we divide it by the ith component of the vector x whenever the ith component of the vector x is non-zero. And claim 7, the Perron-Frobenius eigenvalue R is greater than or equal to the minimum over all I of the row sums sum over all j of aij, and the Perron-Frobenius eigenvalue R is less than or equal to the maximum over all I of such sums, sum over j, aij. Let us also mention some generalizations of the Perron-Frobenius theorem. Definition: a matrix A with non-negative entries is called primitive, provided that some power of A has strictly positive entries. And all claims of Perron-Frobenius theorem extend mutatis mutandis to primitive matrices. Another definition: a matrix A with non-negative entries is called irreducible, provided that it cannot be conjugated to a non-trivial block upper triangular matrix by a permutation matrix. Most of the claims of Perron-Frobenius theorem can be generalized to irreducible matrices, but sometimes with some caveats. For example, there might be several eigenvalues of absolute value given by the Perron-Frobenius eigenvalue R, which coincides with the spectral radius of A. But all these eigenvalues will be simple. What is important to emphasize, which can be easily deduced from our proof of Perron-Frobenius theorem, that if A is a matrix with non-negative entries, then the spectral radius of A is an eigenvalue of this matrix, and there is an eigenvector for this eigenvalue with non-negative entries. And also, if a matrix A with non-negative entries has an eigenvector with strictly positive entries, then the corresponding eigenvalue is exactly the spectral radius of A. Now we can use Perron-Frobenius theorem to define what is known as a Perron-Frobenius character for certain monoidal categories. As before, in the definition of the Grothendieck ring, let C be an essentially small additive and Krull-Schmidt monoidal category with biadditive tensor product. Assume that C has finitely many isomorphism classes of indecomposable objects, and let x1 and so on xn be a complete and irredundant list of representatives for these objects. For any object x in X and two indices I and j from 1 to n, denote by A sub ij upper x the multiplicity of xi in the tensor product of x with xj. This gives us the matrix n times n matrix with non-negative integer coefficients consisting of these multiplicities aij upper x. We denote this matrix by A sub x. Theorem: assume that our category S has a unique cell, which is left cell, right cell, and two-sided cell. Then there is a unique ring homomorphism, which we denote by PF, from the Grothendieck ring of C to real numbers, such that for any x in C, the value of this homomorphism at the class of x coincides with the Perron-Frobenius eigenvalue for the matrix A sub x. Let us prove the theorem. Consider the object y of C, which is given by the direct sum of all the indecomposable objects. Multiplicity-free direct sum is not really important. Denote by Bij the multiplicity of xj in the tensor product of xi with y. Then we have the matrix B, which consists of these multiplicities bij, and all these multiplicities are, of course, non-negative integer entries. However, we have assumed that our category has a unique right cell. So this actually implies that all these multiplicities are non-zero. So our matrix B is a matrix with positive integer entries. And so we can apply to it the Perron-Frobenius theorem. Consider the Grothendieck ring of C, and let us extend the scalars in this ring from Z to R. So let us consider the corresponding ring, which we denote by R. Then we have the regular RR by module R. Now let us look at our matrix B. So this is a matrix with positive integer coefficients. So it has a Perron-Frobenius eigenvalue and the corresponding positive Perron-Frobenius eigenvector. So we can view this eigenvector as an element in our ring R. Note that in the definition of B, we tensored with y on the right, while in the definition of AX, we tensored with x on the left. So because of the associativity of our multiplication in our ring, multiplying our vector W with the matrix of x on the left gives a new eigenvector for B. This is because associativity means that the left and the right multiplications commute. But we know that a positive eigenvector for any matrix with positive entries is unique up to scalar. So multiplication of W with the matrix of x on the left should give us W with some scalar. Let's denote the scalar by R sub x. And now, if we apply Perron-Frobenius theorem to the matrix AX, we obtain that Rx must be the Perron-Frobenius eigenvalue of AX. So we have this matrix AX, which is a matrix with non-negative integer coefficients, but now it has an eigenvector which is W and which is a positive eigenvector, and the eigenvalue is Rx. So by the Perron-Frobenius theorem, Rx must be the Perron-Frobenius eigenvalue for Ax. And directly from the definition, it's easy to see that the map, which takes an object x and gives as an output the scalar Rx, is both additive and multiplicative. And since the classes of the indecomposable objects generate the Grothendieck ring as a ring, it extends to a ring homomorphism uniquely in the obvious way. And this proves the theorem. The map PF, which is given by the theorem, is called the Perron-Frobenius character. Using the estimates for the size of the Perron-Frobenius eigenvalue given by the Perron-Frobenius theorem, we see that the value of our Perron-Frobenius character at any non-zero object of x is greater than or equal to 1. Here is example 1. Consider the monoidal category of all finite-dimensional K vector spaces. In this case, we have one indecomposable object, namely the one-dimensional space K, which is also the identity object. For any finite-dimensional vector space V in K mod, tensor in V with K is isomorphic to V, and this in turn is isomorphic to the direct sum of copies of K, where the number of summons is given by the dimension of V. Therefore, the matrix AV in this basis given by one object K is just the 1 times 1 matrix where the entry is the dimension of V. So it follows that the Perron-Frobenius eigenvalue of this matrix is equal to the dimension of V. Also note that in this case, the Grothendieck ring of the category of finite-dimensional vector spaces is isomorphic to Z, while the map, which assigns to the class of the one-dimensional vector space number 1. So this is a dimension of this vector space. So from this point of view, the map PF in this case is just an isomorphism between the Grothendieck ring of this monoidal category and the ring Z. Example 2. Let G be a finite group. Consider the monoidal category of all finite-dimensional G modules over the complex numbers. Let L1, L2, and so on Lk be a complete and irredundant list of simple G modules. Let V be a G module. Then tensor in V with a regular G module C of G is isomorphic to the direct sum of copies of Z of G, where the number of direct summons is the dimension of V. The list of multiplicities of simple modules in the regular G module is just the list of the dimensions of the simple G modules. And this formula implies that this vector, which consists of the dimensions of the simple G modules, is an eigenvector for the matrix corresponding to V, and the corresponding eigenvalue is exactly the dimension of V. So this is a positive eigenvector for this matrix, so the corresponding eigenvalue must be the Perron-Frobenius eigenvalue. So the Perron-Frobenius eigenvalue for the matrix AV is equal to the dimension of V. In fact, this example is a motivation that in the book of Agneau, the map PF is called the Perron-Frobenius dimension. Let us conclude with some problems and questions. Question 1. Check with all details that our partial preorders, left, right, and two-sided preorders are indeed partial preorders. Question 2. How is the positivity property of the basis used in the definition of these preorders? Question 3. Prove claims 5, 6, and 7 of the Perron-Frobenius theorem. Question 4. Check with all details that the map, which assigns to an object x and c the scalar Rx in the proof of the theorem about the Perron-Frobenius character, that this map is both additive and multiplicative. And question 5. Prove with all details that tensor in a G module with the regular G module, we will get the direct sum of a number of copies of the regular G module, where the number of summons is the dimension of V. Thank you very much, and see you next time.